So, hello everyone. Today we'll be discussing Lasso and regression along with its applications in data science. So, let's begin. So, first of all, answering why we need to study it. Okay, so whenever you are working on a machine learning algorithm or any machine learning problem, you can face two problems, which is a bad data or a bad algorithm. So we are not going to discuss about bad data, but yeah, sometimes you have less data, or you have many outliers or not proper data. So that's another issue. We are not going to discuss that. So bad algorithm. Also in bad algorithm, you have one issue, overfitting, which is our primary focus of discussion. So in overfitting, what is overfitting basically? So overfitting is like you are kind of overgeneralizing things, making simpler things complex, or in terms of a model, when the model memorizes the training data, it performs well on the training data obviously, but it doesn't on the new or unseen test data. So let's say here it's written, it's kind of example. Say you visit a foreign country and the taxi driver rips you off. You might be tempted to say that all taxi drivers are thieves. Okay, this is overgeneralizing. Okay, so similarly for machines, it is overfitting. So this is an example of a classification model where this curve, it's clearly an overfitting, because it is performing like kind of perfectly well on the train data. Okay, so not I mean, this is a clear case of because it is completely overgeneralizing it. Okay, so this is an example of overfitting. Overfitting happens when the model is too complex relative to amount of noises on the training data. So let's say once I was working on a problem where you have a country's name, its inflation levels, its industrial growth, and the repo rates, and lots of countries' economic data, and you need to predict the GDP or probably some index. So what happened was that this neural networks, they find trends in even they try to find trends in every features, even in the noises. Even in the noise they find patterns. So what happened was that they in that case it found a pattern that countries with name Z, generally countries with that have letters Z in their name, are generally having good GDP. So like New Zealand, Switzerland, and many other. So but in the case of Zimbabwe, the actual data, like it was a huge variation in the prediction because of this pattern. It was not a logical pattern, but the complex models like neural network, they do these things. Okay, so you need to be aware of it, and so you need to prevent overfitting. Okay, so that's the fewer degree of freedom. Okay, degree of freedom is basically let's say you have two features and which are unconstrained, you have degree of freedom 2, but let's say you fix the value of one of them, then you have a degree of freedom 1. Okay, and let's say you have constraints on one of the, like it should be between 1.1 and 7.2. Let's say then this is constrained, then the degree of freedom reduces to, let's say, 0.5, 0.6, some kind of thing. Okay, it's not much related to our discussion, but still. Okay, let's move forward. So the less the degree of freedom, the less are the chances for overfitting. Okay, solution. So there are many solutions to reducing overfitting, like getting more training data, reducing noise. Okay, we'll not focus on that. We'll focus on regularization. So regularization you can think of as simplifying the model along with minimizing the cost. I'll explain you this. Let's say a good fit to model is, okay, omega 1x squared plus omega 2x squared, omega 1x plus omega 2x squared plus b, and the corresponding overfit would be, because overfit, it would try to fit on every data point in the training set. So it would obviously add more terms with higher degrees, and I'm sorry. So this would be the overfit. Okay, so what our aim would be to minimize this omega 3 or omega 4. So keep the values very close to 0, so the effect is kind of negligible. So for that we have two methods, L1 and L2 regularization. Okay, so we'll see that. Regression. Okay, so here you modify the cost function by adding this term, lambda times summation I 1 to n theta I square, where theta are the parameters omega 1, omega 2. You can relate it with that. So what it does, it penalizes for each large omega. the cost function, so you would try to minimize the cost function, so you need to keep this value small, and if I increase the value of lambda too much, then this value would be very close to 0, because our aim is to minimize the cost function. So we'll see that this forces the learning algorithm to not only fit the data. Yes, obviously we can can't diverge too much. Okay, like overfit model would be like exactly fitting on the line. You can imagine a line like, let's say y is equal to 2x. Every training data is on this line. Okay, just assume it for simplicity. So what our aim would be, to find a line around y is equal to 1.7x. Okay, which is near to, which is fitting the data. It's not like you can't say y is equal to 100x. Okay, so it should fit the data, and also the model weight should be minimized, so that it doesn't overfit. It performs well on the new unseen test data also. So note that the regularization term should only be added to the cost function during training. Okay, again, while testing you will use the old cost function. Okay, not this new modifier. This is just for training the data. Okay, once the model is trained, you want to evaluate. Okay, that's what I explained to you. The larger the lambda, the stronger the punishment. Okay, yeah, because you need to minimize, and if this term is lambda, this is too high, so these terms would tend to 0, or very minimized. They would be very much minimized. Okay, as the value of lambda increases, the coefficient gets smaller and approach 0. But remember, in case of L2, they would never be exactly 0. Okay, they would be very close to 0.0, that is 0.001 or something like that, but they would never be 0. Why? I would explain you with the curve in the next slide. This means all the predictors are retained. Okay, so we are not eliminating any feature completely, which happens in the case of L1 regularization or Lasso regularization or Lasso regression. Okay, this is what written here, which can eliminate certain predictors by setting their coefficients to 0. Okay, why? So you can see this curve. So in L2 we have a lambda times omega 1 square plus omega 2 square. They have called it beta here. So this is that additional regularization term, and this is our cost function. These are the contours. So each this circular curve is one constant cost for different combinations of parameters. This is another constant cost curve for different combinations of parameters. So when this two would intersect, so this is the minimum point. Okay, minimum cost point, and as you move far, the cost increases. So this intersection point would be the optimal solution. So you can see that here it must one parameter must be 0. Here beta 1 is 0. So when you visualize it in more dimensions, you will see that always some parameters would be 0, which is not the case here. Okay, they would be close to 0 but not exactly 0. Okay, so yeah, for ridge regression you have this formula. Now how this comes, I will explain you. Okay, so we have equation AV is equal to y, let's say. Now how this comes, so actually this annotation tool doesn't work very good on Mac, but I will try. So let's say you have 100 data points, 1 2 3 4, which 4 features, 1 2 3. This is the fourth one, is let's say predicted. So this whole matrix, this would be your A matrix, right? You would multiply this with parameters like this one with omega 1, this one with omega 2, this one with omega 3, let's say, kind of, and this would lead to a predicted value y, which is our fourth feature, this one. Okay, right? So you can now see that it's AV is equal to y. So we'll define our cost function in matrix form, which is y minus AV transpose into y minus AV, which is equivalent to y predicted minus y actual the whole square. Okay, just in matrix form, it's plus lambda v square. Okay, we are discussing for L2. So now phi is when you open up this matrices, it's this. Okay, now this y transpose y is a scalar. Can you see it? Because actually when we'll store it as a y, just a minute, y transpose. Okay, y transpose would be 1 into 100, right? And y would be 100 cross 1. Okay, isn't it? So isn't this a single value scalar? So by the property, scalars can be added to scalars, 1D tensors can be added with 1D tensors. So this is a scalar. So this is a scalar. Every term is a scalar. So using this property, you would find out that you can take transpose of this term and it would not be affected. So using this all properties, when you differentiate, you get this. Okay. And when you equate it to 0, you have the solution. V is A transpose A plus lambda I inverse A transpose Y. This is what I have written in this slide also. A transpose A plus lambda. Here you can use alpha S inverse A transpose Y. Okay. S is the same matrix as I actually. See, in our formula it was I. But the point is that some data scientists like Andrew Ng, Professor Andrew Ng, he says that instead of I, he uses a matrix. Like the first term he keeps 0 and 1 1 1 1. So he uses basically I only, but he keeps the first diagonal element as 0 and he calls it as S. So it's fine, we can use S also, but okay, it's I also is also fine. Okay. It's just small point, it doesn't matter much. Okay. So for coding part we have this. I will show you later. I have code written, we'll see the code also. Okay, before moving to that, cross validation. So what is cross validation? I will explain you a little. Okay, so cross validation is a technique, I have used it in the code, so I will explain it a little. It is used to have low bias. So what we will do is, like, you see the cost function. Okay, so lambda, we don't know, this is called a hyper parameter, and we have our training data set, let's say 1000 points. Okay, so first of all we need to divide it into train and test data, right? You can split it according to 20%. So it's 20%, 800 points in training, 200 points in test, probably you can split it like this way. So now here there are certain points. First of all I would like to explain random state. I have used this all terms in my code. So let's say you have 10 points, we'll explain it with simpler, and you want to split it like 7 to 3. 7 is for train, this is for test. So you can have different such combinations. Out of 10 points, any 7 can go up here, any 3 can, this different combinations for this. And here the combination number 42, I would take that data. Okay, so if I use random state 42, it means that the 42th combination would I would be using that. Okay, so that's about random state. Just a minute. Okay, leave it. We'll use new one. Okay, so yeah, I was talking about this. We split it. Okay, it's 800 for training, 200 for test. Now if you use cross validation, you have n folds, which is, or you can, it is called k fold validation. I will take up a new slide, just a minute. Okay, k fold validation. Damn it. So what you do is, like, you have, let's say 100 data points and you want to split it into 80-20. So either you can take this first 20 as your test data and the next 80 as your train data, or you can take the first 20, the next 20 and the next 60. So this 60, this 20 and this 20. So this would be the test, this would be the train. You can have such many combinations, and that is what is defined by n folds. So k folds. So what here it would, if I let's say set k fold, k is equal to 5. So for each parameter, hyperparameter, let's say for lambda 2, this model would be trained 5 times. The first time, the first 20 would be test, rest 80 would be train. The next time, this intermediate 20 would be test. So such different 5 combinations would be taken. Every time the model's performance would be tested. In whichever case the the performance is best, that score would be scored. So for lambda 2, the score something, let's say 67 is the best score. So this way it would be scored. Then we will see for lambda 3 again, following same procedure, we would note the score, let's say 62. For each lambda we would repeat this procedure. That's how cross validation and these things work. Okay. So this is what, I explained the same part. Okay. And you do cross validation with function, which is grid search CV. Okay. It tries all the combinations of value passed in the dictionary and evaluates the model for each combination. This is what I explained you. Hence, after using the function, we get accuracy loss for every combination of hyperparameters, and we can choose the best. Okay. I explained it completely. Okay. Now Lasso. Okay, in Lasso it's just kind of similar, but the cost function is just lambda times mod of v. So for minimizing it, one of the some parameters must go to 0, which is also visible from this. Okay, so we'll read it once. Lasso least absolute shrinkage and selection operator. Okay, its full form is another regularized version of linear regression. It's just like ridge regression. It adds regularization term, but it uses L1 norm, and whereas ridge used L2 norm. Okay, and important characteristics, it eliminates the weight. Okay, this is what I explained. So this can be used in feature selection also. Okay, where you need to keep up the just important features, so it can eliminate the unnecessary features. So this can be used in feature selection also. Okay, we'll come to this conclusion. First of all, we'll see the code part. Okay, I'll just open the code part. So hello everyone, now we are going to see the code part. Okay, so these are the necessary libraries. I have got an insurance data, and this is just one hot encoding. Okay, so see, this is the data: age, sex, BMI, children, smoker, region, and charges. So I first of all encoded this one, like I converted to ones and twos. Same for here, same here. Okay, now I got my x and y. So this is x 1338 cross 6. Okay, and this is y. This one. I mean this charges. Okay, now I split the data. Okay. Random state I explained already. Now if it's a linear regression model, I trained it, I predicting a value, score on test, on train, and the coefficients. So this is the score. It's 78% accuracy on test, which is actually good. So now I don't think that there's need for regularization. Okay, so you can see if it performs poorly on the test data and good on training data, you may feel the need for regularization, but I don't find it here. So anyways, we'll see. The coefficients are okay: omega 1, omega 2, omega 3, omega 4, omega 5, omega 6. Okay, now I'm importing Lasso regression. This is the range for alphas. I have paired them, created dictionary. This is n folds 5. Model is Lasso. This is grid search CV cross validation, which I explained already. This is 5-fold, if you can see. I am fitting X train, Y train. I am predicting a value, score, okay, optimal alpha value, and the coefficients. So here you can see a warning that I am not scaled them or I have less iterations, but that's fine. Actually, we will not go into that. It's okay. So the value is 25185 and it predicted 25242, so it's close. The score is again nearly kind of similar, only 7874. Okay, and these are the optimal values. These are again also similar, I guess, but see 257, 236, 27, you can see. But actually you see it made one value 0, which is compulsory for Lasso. I told you that. See, it's compulsory. I mean, not compulsory, but Lasso regression works that way. So here it's 0. Okay, now we'll see ridge regression. Model is ridge, same code, just we have made ridge. It's predicting the same value. Again you can see 78, 74. So it's, I told you the model is already working good on the default linear regression, so it doesn't need much of regularization. Okay, and now here the FTL values are again close to the original parameters, and no one's exactly 0, which I already told you, because that's not the case in ridge regression. Okay, now here's an interesting thing. You can see we see the formula, right? This one. Now I got the parameters in two different ways. You see, one way I got, I predicted the coefficients, like dot coefficient method, and I got these values. Okay, so you can see this all are values like 256 something minus 11 hours. This is 335. Now what I did is I used directly this formula. I mean, I can find the parameter values using directly this formula also, why not? So I did just the same. I mean, why to train model and do all that stuff? You have this matrix, you just so I created a matrix, diagonal matrix, alpha. This was the best alpha from ridge regression. I used that alpha. I created a X transpose X, added alpha into diagonal matrix, took its inverse into A transpose into Y, and answer. But you can see the values diverge largely. 10 to the power 15, 13, 15. Oh my god. You see? And why is this happening? So I will leave this to you. I will end my video here. It's a topic you should ponder upon, but I will give you a hint. This condition number, try printing the condition number for this matrix whose inverse you are taking. So think upon it, and I will last conclusion. So sometimes it's necessary to think before applying certain method, that whether we should apply regularization or not, because okay, so there are some points whether to apply or not. So see, if your data is small, this techniques can be helpful. Okay, and you are not able to get more data, then you should apply this techniques. Model complexity. If your model is complex with lot of features, okay, large number of parameters, and especially the parameters are large, like deep neural network, regularization, it's most likely to that you will apply, and L2 is generally used. Okay, feature importance. If you have many features and you want to, this is what I told already. Feature selection, L1 helps in feature selection because it would make some coefficient 0, so effectively eliminating those features. Okay. Outliers. So if your dataset contains outliers or noisy data points, L2 can help. Okay. And collinearity, if there is a multicollinearity in your dataset, that is, there is high correlation between two features, again L2 can help in reducing their effects. So this is all, but like the seeing the data set, you cannot say whether you should apply or not. I mean, you need to either apply the linear regression model and check the score, then you can definitely tell whether you should apply or not. And these are some other points: seeing the data set size or the complexity or the features, number of features. You can get a brief idea that whether you should apply or not. But actually, when you just test the linear regression model and check the score, then only you can tell. Okay, so that's all. These are the resources. And okay.